Okay, this is the lecture video for MAC1140 Pre-Calculus. This is section 4.7, and in this section we're going to be looking at complex zeros and various operations that can be performed with those type of values, as well as the fundamental theorem of algebra and various other definitions and corollaries that relate to that theorem. Okay, so let's get started with just a little review of what a complex number is. A complex number is part real and part imaginary, but any complex number may have the real portion being 0 or the imaginary portion being 0. So you can have a complex number that is just all real, in other words, the imaginary portion is 0, or you can have a complex number that is purely imaginary and the real portion is 0. So all three of these classify as complex numbers. In other words, real numbers as well as imaginary numbers are subsets of complex numbers. And we have some examples here. Just states what I just said verbally. And we're going to go into the first operation that we can perform. You can find sums and differences for complex numbers, and when you do so, you're simply going to combine. It's like combining like terms. You're going to combine the real portion with the real portion of the other complex number, and then you will combine the imaginary portions. Here is an example. In example 1, we're also going to be looking at finding products where we're going to FOIL. And I want you to remember that as you do find a product, you're going to get a term that has I squared in it. And please remember the definition of I squared is -1. Okay, so in example 1, we're going to find the sum and the product of these two complex numbers, 3 minus 5i and -3 plus 7i. So I've already written out the sum. Here is 3 minus 5i. We're combining it with -3 plus 7i. And this is just like combining like terms. So we're going to combine real with real. 3 plus -3 would get rid of these portions. And then when you combine the imaginary portions, you get 2i. So the sum of these two complex numbers is 2i. It's purely imaginary. Okay, then we're also going to find the product. And in that case, we're going to FOIL. So we're going to take the first complex number and multiply it by the other complex number. And we're going to FOIL here because we're multiplying a binomial times a binomial. So we're going to go first times first, FOILing, outer times outer. I'm just reciting what each letter of FOIL means. Inner times inner, and then last times last. Okay, let's go ahead and follow those arrows, finding the product each time we do so. We're going to do the upward arrows first. First the short one, then the long one. So 3 times -3 is -9. Then we're going to go 3 times 7i would be 21i. Then we're going to do the upside down arrow, short then long. So we're going to go -5i times -3, and that's positive 15i. So you have two imaginary terms in the middle. And then that last arrow is going to be -5i times 7i, which is -35i squared. Don't forget, I squared has a definition. And that is that I squared is equal to -1. So don't forget, you're going to have to replace that I squared with a -1, which turns it into positive 35, which means it is now a real number, which can be combined with the other real number up at the front. Okay, so continuing with this problem and combining like terms, we have -9 plus 35. You can put that in your calculator if you like, and that is 26. Then when we combine the two imaginary terms, we have 36i. Okay, so we've just taken two complex numbers, just a little review of how to find a sum as well as how to find a product. Okay, moving to the next example, we're going to look at a couple of theorems before we do so. I wanted to let you look at the definition of complex zeros. Remember, zeros are solutions for an equation. So when we use the word zeros, think of the fact that you are finding solutions. And we are specifically talking about in this section how to find zeros of a complex nature. So a variable in the complex number system is referred to as a complex variable. A complex polynomial function of degree n is a function of the following form, where a sub n minus 1, the coefficients they're talking about, are complex numbers. The leading coefficient, which is a sub n, cannot be equal to 0, and n is a non-negative integer, where x is a complex variable. As before, a sub n is the leading coefficient. I already said that. A complex number r is called a complex zero if f evaluated at r is equal to 0. So the entire section is going to be about various techniques used for finding complex zeros. Okay, we also are going to be using, as we look for all of these zeros, the fundamental theorem of algebra. And this theorem states that every complex polynomial function, and I just introduced the definition of a polynomial function, of degree greater than 1 has at least one complex zero. And you're going to see that as we begin looking for those complex zeros. Another theorem regarding complex polynomial functions: every complex polynomial function of degree greater than 1 can be factored into n linear factors, not necessarily distinct. So there could be some factors that repeat. Conjugate pairs theorem. This states that if f is a polynomial function whose coefficients are real numbers, and if r is a complex number, is a zero of that function, let's say a complex number of this form happens to be a solution of the function. I'll just reword it using words that are more familiar to you, but we want to be, we want to start using the word zero in place of the word solution, just so you have an understanding. So the complex conjugate, so what we're saying is if the complex number a plus bi happens to be a solution of the function, then so is the conjugate, and that's what the conjugate pairs theorem states. So if you find that 2 plus 3i is a 0, then 2 minus 3i is also a 0. A corollary that stems from the conjugate pair theorems states that polynomial function of odd degree with real coefficients has at least one real zero. And you're going to see when you get into my math lab that they're actually making questions out of these theorems. So you have them here in your outline, and you can refer back to these theorems and corollaries in order to answer some of the questions. I mean, most of the questions you're going to be applying these actual theorems and using them in various mathematical operations to find the zeros. Okay, so in number 2, all it's asking is if you understand what a conjugate is. Okay, you have a complex number here, part real, part imaginary, and they want you to find the conjugate. That means switch the sign of the imaginary portion. So the conjugate would be -2 minus 5i. Okay, and number 3, if 7 plus 5i is a 0, okay, if 7 plus 5i is a solution of a polynomial function of degree 5, the degree really doesn't matter, with real coefficients, then so is 7 minus 5i. Okay, and that comes from the conjugate pairs theorem. Not that you have to write out the theorem. You don't have to write out the name of the theorem in MyLab Math when you do the homework, but I'm just telling you that's the theorem that we just went over up here, that if any particular complex number is solution, then its conjugate is also a solution. Okay, so yet to work anything out. Now finally we get to example 4, and it says use the quadratic formula to find complex solutions for the second degree equation. Solve the equation in the complex number system. So you've had experience with this, finding using the quadratic formula when it can't factor. This cannot be factored, so you have to use the quadratic formula to find the solutions, and they just happen to be complex. Okay, here we go. Remember that this is the quadratic formula, opposite of the b value plus or minus square root of b squared minus 4 times a times c all over 2a. And we're going to apply that quadratic formula in order to find the complex zeros here. Okay, so the a value here, just to review, is 1. The b value is this number right here, -2, and then this is the c value. Okay, so the solutions for x in this problem are opposite of the b value plus or minus b squared minus 4 times a times c all over 2 times a. So that ends up being +2 plus or minus, you can work this out a little bit, this is 4 minus 8. Okay, and so now we're going to just continue. I did a little bit of the work over here. So 4 minus 8 is just -4 over 2. I can shorten this up a little bit. And this is going to be equal to 2 plus or minus. And then the square root of 4 would be 2, but square root of -4, anytime you're taking the square root of a negative, there's an I involved, and the I comes to the outside of the radical. So the square root of this would be 2i over 2. 2 divides into this, this, and this. It would be 1 plus or minus 1i. 2 divides into that once, and into that once, and into that once. And you know that when the denominator is 1, you don't need to report it. So that's the final answer there. Okay, that takes us through example 4. Let's move to the next page. Give me 1 second. Okay. Now let's move on to example 5. Okay, so in example 5 it says, determine whether the statement is true or false. A polynomial function of degree n with real coefficients has exactly n complex zeros. So in other words, just whatever the degree is, that's how many zeros there are. And that was, I'm telling you to see the theorem at on the previous page. That was this one, and it says it right there at the bottom of the theorem. Anything with degree n greater than 1 has exactly n solutions. The degree determines how many solutions there are. And that's probably something that you're very familiar with. Really make a point of that so that the student knows how many solutions to look for. Okay, so this is true. Okay, example 6. Decide whether the statement is true or false. A polynomial of degree 4 with real coefficients could have the following zeros: -3, 1 plus I, there's its conjugate, because every time you have a complex 0, its conjugate should also be amongst the solutions. And then you see that this is a solution, negative 3 plus 7i, but yet they do not mention negative 3 minus 7i, and that needs to be a solution. So is this true or false? It is false. And that's because if negative 3, and this is from the conjugate pairs theorem on the previous page, if negative 3 plus 7i is a 0, then negative 3 minus 7i also has to be 0, yet it is not mentioned here, and that's why it's false. In example 7, it says information is given about a polynomial whose coefficients are real numbers. Find the remaining zeros. Okay, if it's degree 3, and we spoke about that right here, that whatever the degree is, that's how many zeros there are, and that applies in this problem. So if it's degree 3, there has to be 3 solutions, or 3 zeros. And you can see here that they're giving you a real 0, a complex 0, and then of course its complex conjugate needs to also be a 0, because the complex solutions, they always come in conjugate pairs. This would be the other one, negative 1. Switch the sign in front of the imaginary term to get the conjugate. Remaining 0 is negative 1 plus I, which I stated there and there. Example 8. Form a polynomial function. Now these are quite a bit of work, so here we go. Form a polynomial f of x with real coefficients having the given degree, so it's going to be 4th degree, so there should be 4 factors, and having the given degree and zeros. However many zeros there are, however many solutions there are, all of the solutions come from factors. So what we're going to try and do is take these zeros and write them in factored form and then multiply them out. Okay, that's going to be our approach here. Use the zeros to write the factors of f of x, and then multiply them out. So here we go. I don't know what the leading coefficient is on this particular function, so I'm just going to call it a. And I believe that they're probably just going to have an a in my math lab. They're not going to make you go as far as finding that. Okay, the factors come from the zeros. So one of the factors, they said one of the zeros is 1. Whatever the zeros are, they appear using the opposite sign when they're in the form of a factor. So if you want to write the factor that corresponds to positive 1, it is x minus 1. Each factor starts with an x, and then it will use the opposite sign as the 0. So this factor is corresponds to a 0, 1. It would actually give you a solution of 1, this particular factor. Now it says that this 0 has a multiplicity of 2. That means the factor has a power of 2. Okay, then it also says that 6i is a solution. Now this gives you 2 of the solutions. You just have a solution that happens to repeat. You would get the solution, or the 0 as they call it, x equal to 1. That is what would 0 this out. Or in other words, what's the solution? But that it just so happens that that solution repeats twice. That is what it means to have a multiplicity of 2. The other thing is that we still need to have 2 more factors. This is 2 factors, x minus 1 times x minus 1. We still need 2 more, and they're going to come from the conjugate pairs theorem. If 6i is a solution, or a 0 as they call it, then so is negative 6i. So now when you put them in factored form, it goes x, and just putting a minus here will make the sign on this switch. So that goes from positive 6i, but appears as a negative 6i. Then we'll do another factor. Just putting the minus right after the x will cause the sign to switch. So this is going to go from a negative 6i, it appears like that when you first plug it in, but eventually it'll be a positive 6i when you rewrite the double negative. So this will be x plus 6i. This will be x minus 6i. And then this will be the factor x minus 1. Again, you put an x, then a minus, it'll automatically switch the sign that the zeros have. And this had a multiplicity of 2. We do not know what the leading coefficient is, but our job is to get this multiplied out. So, from the appendices where we were reviewing how to FOIL and how to use the shortcuts, now's the time to employ the shortcuts. You really need to pull those out so that you're not making this into twice the work. What you see right here, squaring a binomial, and you need to memorize the shortcuts. The shortcut for squaring a binomial is to go square, double, square. So in this case it would be, let me put that leading coefficient. Let me move this over a little bit. And put f of x right here. There's my equal sign, my a, and here I go. I'm going to square, double square. Okay, you square that first term. Keep it in parentheses. Doubling means multiply this times this, negative 1x, but then double it. You'd have it negative 2x, and now square again, but this time square the back term, which is that negative 1, and you get positive 1. So when I FOIL this out, I get x squared minus 2x plus 1. Now we want to FOIL this out. And because these are conjugates, this also has a shortcut. And that shortcut is square minus square. I'm going to keep writing out the shortcuts every time I use them to try and help you memorize them. Okay, whenever you are squaring a binomial, it's square, double, square. And whenever you're multiplying conjugates, it's just square minus square. And when you do square minus square, you could either look at this one or this one, doesn't matter. You'll get the same answer either way. Okay, here we go. We're going to do square minus square. So we're going to square that first term, and we're going to square that second term. So this squared would be 36i squared. You have to square the 6 as well as the I. So 36i squared. Don't forget to put a minus in between the two squares. So we have everything FOILed out, but we still have quite a bit of simplifying to do. Like for instance, this right here would be actually positive 36 because it's negative 36 times negative 1. So let's bring that up here and continue to multiply. And at the end, we'll get rid of these brackets and just put a pair of parentheses. But while we're working right now, we'll just leave it like this. Okay, so this is going to be, now this is only going to have two terms in it. This and the x squared and the positive 36. And this has three terms in it. And you do have to FOIL these out. You're going to have to multiply a binomial times a trinomial. And you're better off having the factor with less terms in it at the front so that your arrows don't cross over each other. Okay, so this is going to be x squared, this is positive 36. X squared plus 36. I'm going to put the shorter polynomial at the front and the longer one at the back, which has the x squared minus 2x plus 1. Okay, continue, because remember, you're trying to come up with the polynomial that had a zero that was a 1 with a multiplicity of 2, and then zeros of negative 6i and positive 6i. We're trying to get all the way to a polynomial that doesn't have all these parentheses and brackets. So let's continue. We're going to FOIL now. We're going to go x squared times everything in this second parenthesis. And then we're also going to go 36 times everything in the second parenthesis. Okay, so x squared times x squared was x to the fourth. Then x squared times negative 2x is negative 2x cubed. Then x squared times 1 is x squared. Now we're doing all the upside down arrows. 36 times x squared. 36 times negative 2x. And then 36 times 1. I don't know if I can squeeze all that in there. Okay, so let's keep going here. Let me just write this a little bit better and also combine like terms. And you can leave these brackets, or I'm just going to replace them with parentheses at this point because I'm going to be finished now on this step. Okay, so since I've gotten rid of all the parentheses on the inside, I'll just use my grouping symbols as parentheses because brackets and parentheses are both grouping symbols. So here we go. X to the fourth. On the x cubed term, I only have that 1 cubed term. Now I'm going to start combining like terms. I can put those together and get 37. And then I can also list the 72x and the 36. And that's my polynomial. It is a fourth degree polynomial, just like they said at the beginning, and it has all of these zeros. Okay, pretty long problem. That's one of the longest ones. Okay, use the given 0 to find the remaining zeros. This also has quite a bit of work. Okay, so here we go. If this is a 0, according to the conjugate pairs theorem, then this is also a 0. And don't mind me, sometimes I make my 4s like this and sometimes I make them like that. Undecisive, I guess. Okay, so what you can do, what you want, we're going to have to use long division here. The first thing you're going to have to do is recognize by the conjugate pairs theorem that if negative 4i is a solution, then so is positive 4i. And just from this, you can get a factor that we can divide into this. So we're going to create, just by knowing that these are zeros, we can create these two factors. X minus negative 4i and x minus positive 4i, which turns out to be x plus 4i in the first parenthesis and x minus 4i in the second parenthesis. And once you get to that point, you could actually multiply these out because we want a factor that we can divide into this original polynomial so that we can get the other factor and then end up finding all the solutions. Right now, we know that this is fourth degree and we already know 2 of the answers. We still have 2 more answers to find, and we are going to find them by ultimately factoring, but we're going to have to get to the factors through division. So, not such an easy problem, but here we go. What are we going to divide into this? So we're going to go, now notice that these are conjugates. So yes, you could FOIL it the long way, but you should be using the shortcut. The shortcut anytime you're FOILing out conjugates is to square minus square. Cuts down on a bunch of work. So square the front term, square this back term, and then throw a minus in between the 2 squares. That is the same thing as x squared minus 16 times negative 1 is positive 16. So this is a factor. In other words, it divides into, anything that's a factor divides into whatever it's a factor of. This is a factor of h of x. Okay, so if it's a factor, that means we can divide it into this original polynomial. 4x to the fourth, 7x cubed, 62x squared, plus 112x minus 32. Get rid of this word right here because we're going to need all the room we can get. Okay, so now what you're going to do once you get this is divide x squared plus 16 into h of x. Okay, this is h of x right here, and we are going to divide what we already know to be a factor of h of x. We're going to divide it right into h of x. So remember that when you're dividing, you ask yourself, what does this first term have to be multiplied by to turn it into this term? And that would be 4x squared. Once you come up with a single term in the quotient, you multiply it by everything out here in the divisor. So it's 4x squared times x squared, 4x to the fourth. 4x squared times 16, that would be 64x squared. And make sure you line it up with the correct column. It has to be under a like power. So 64x squared would go right here. Third step, so first you find a single term of the quotient, then you multiply that term by everything in the divisor. This was reviewed in a previous section, one of the appendices, and then you subtract. And you keep going until you can't repeat those three steps any longer. You're subtracting the entire bottom row from the top row, which just means switch the signs on the terms in the bottom row and combine them with the terms above. So this combined with this, gone. 62 take away 64 is negative 2x squared. Bring down that positive 7x cubed and bring down the 112x. I don't think we're going to need the negative 32 yet, but eventually we will. Okay, go again. As long as this power is less than this, you can go again. So what do you have to multiply x squared by to get 7x cubed? You'd have to multiply 7, and you'd need an additional x to turn it into that. So 7x. Okay, we now have our second term in the quotient. Now multiply it by everything in the divisor. So 7x times x squared is 7x cubed, and then 7x times 16, that's 112. Yep, 112. So 7 times 16 is 112x. That's going to go right here. It's the column that it belongs in. And then the subtraction step. Just switch the signs of the terms in the bottom row, combine them with the terms above them. So this is gone. And then 112 take away 112, that's gone. Bring down that negative 2x squared. And also bring down, let's see, what else have we not brought down? The negative 32. Okay, we can still go one more time. So what do you have to multiply this by in order to get this? Negative 2. Okay, we now have our third term in the quotient. Every time you get a term up here, each time you get a term, you multiply it by all the terms in the divisor. So negative 2 times x squared is negative 2x squared, and negative 2 times 16 is negative 32, and then we go through the subtraction step. So this turns into a positive, this turns into a positive, and if what we created here wasn't a factor, it wouldn't be zeroing out. Since it's a factor, that's why this is zeroing out. So this cancels, you have nothing left. So what you've just done now is you have written this in factored form. That h of x that we started with, it can be written in factored form like this. We have found one of the factors just from creating it from these two imaginary numbers. And that factor was right here. So h of x can be written as x squared plus 16. And then we divided that into h of x and came up with the other factor, which is 4x squared plus 7x minus 2. So there it is in factored form, and then let's take a look at those instructions one more time, make sure we've done everything. Use the given 0, which was just this one, but we knew from the conjugate pairs theorem that if this was a 0, so was this. And that's what allowed us to create this factor that we divided into the original function in order to get the other factor. Now we have it completely factored, and the solutions all come from the factors. Just like this and this come from this factor, there are solutions that come from the factor 4x squared plus 7x minus 2. So what we could do at this point is we could try to factor this, because if you factor it further, you can possibly find the other two solutions. This is fourth degree, so it has to have 4 solutions, or what we call 4 zeros. This is 2 of them. We're about to find the other 2. I'm going to try and factor this, but if it doesn't factor, then I'm going to use the quadratic formula to find the remaining zeros, okay? This is what you're trying to do. You're trying to find the remaining zeros off of this factor that we just found through division. So I think this factors. I believe that if we go 4x times x, that's one way to break this down into factors. I mean, you could go 2x times 2x, but I don't believe that will help us to successfully factor this, so I'm going to try, and that's because I see that we're trying to get a 7x in the middle, and I'm thinking about how I check whether I have factored properly by foiling, so I got that going on in my head as well. I know that 4x times x will get me 4x squared, and if I put a positive 2 back here, now I'm using the guess and check method to get this factored, where you're simultaneously thinking about foiling and breaking up certain terms. You know that to fill in the front position, you're breaking up this term. 4x times x is 4x squared. And in the back, you're factoring this number. So let's see, if I let that be a negative 1, let's check it. 4x times x, 4x squared. 4x times 2, 8x. Minus 1x brings you down to 7x, and that negative 1 times 2, I just factored that properly. And from those two factors that you see that I got from the 4x squared plus 7x, I can actually get the last two solutions, or what we call zeros. This right here, I'll put it over here. If I wanted to find out what makes this 0, I mean, that one's obvious. What makes this 0? Negative 2. That may be obvious to you also, but if it's not, here's the work over here. You would bring the 1 over here, and then you divide by 4 to get you x equal to 1/4. This you can just tell by observation that it's negative 2. Find the remaining zeros. These are the remaining zeros. I know there's a lot of work there. Just highlight this for you so it doesn't get lost in everything we did. It's a lot of steps. So those are pretty heavy problems, numbers 8 and 9. But you're going to see them in my math lab. I am getting these problems from your homework, so you can get a taste of what you're going to see when you actually sit down to do the homework. Okay, moving on to number 10. Find the complex zeros of the following polynomial function, and then write the function in factored form. Okay, you can start the factoring process. Again, this particular factoring algorithm, how to factor the sum of cubes, that was in the appendices that we started the course with, the review work. These factor like this, if you recall. You'll have a short polynomial and then a longer one. One will be a binomial, the other one's a trinomial, and there's a specific algorithm to this. When you are factoring the sum of two cubes, that's a cube and this is a cube. 5 cubed is 125. You take the cube root of the first term, I'll call it cube root 1. You take the cube root of the second term, I'll call it cube root 2. And then you take these two terms and you square, multiply, and then you square. Okay, here we go. Cube root of this term, x. Cube root of this term, 5. In the first parenthesis, this sign will match the original. Okay, then we're going to get these three terms by just using these two cube roots that we just found. You are going to square that first term, multiply the two terms, and then square again, but this time the back term. The way the signs go in this back polynomial is this sign is the opposite of that, and these squares are always positive. Okay, so we have it factored using the algorithm for factoring the sum of two cubes. And then if I read the directions, this says find all of the zeros. Find the complex zeros. Whether it's a real number or an imaginary number, they're all considered complex zeros. So let's see. That one's easy. Take what's in the factor. What would make this 0? You don't really even need to do what I'm doing now. You could just tell what I would plug in to create a 0 here would be -5, but that also comes from just solving this. So there's one solution. That was the easy one. And then this one, you are not going to be able to break it down any further, but you can find the solutions of something that won't factor any further by quadratic formula. So that's what I'm going to do. So I'm going to use x squared -5x plus 25. I would like to know what makes this 0, and so I'm going to use quadratic formula. The solutions for this, or what we call the zeros, are equal to opposite of the b value. Remember, this is the b value, this is the c value, and then the a value is the coefficient of the x squared, which happens to be 1 this time. So opposite of the b value, plus or minus, and then it's b squared minus 4 times a times c all over 2 times a. Okay, keep going with that. It's +5, opposite of a negative. Then I'm going to do a little bit of work right here. This is 25. This is -100. 25 take away 100 is -75. Over 2, keep going with that. I'm going to take a partial square root here. This is 3 times -25. Okay, so it's going to be +5 out there, plus or minus. Here's what I'm taking out of the radical. I'm going to take the square root of -25, which is 5i. When you have a negative underneath a square root, that gives you an i that can be removed. So it's 5i that's being removed, while the 3 is staying underneath the radical, and the denominator's 2. Okay, so we now have the other two solutions. If you want to write them separately, which may help you to do what you have to do as the last part of this problem, they want you to use the zeros that we've just found, these complex zeros, 5 plus 5i times the square root of 3 over 2, and 5 minus 5i times the square root of 3 over 2, to write this in factored form. We already have it in partially factored form. We want to factor this, which can only be done by finding the solutions first and then going and writing it in factored form. Okay, so let's see. These two solutions, if you look at them separately, one of them is 5 plus 5i times square root of 3. Just think this will help you on the next step. And the other one is 5 minus 5i times square root of 3 over 2. Okay, so the function in factored form is the first factor that we found when we factored the sum of two cubes, so that was x plus 5. And now, since we could not factor any further using algorithms, we kind of went in the back door. We found the actual zeros of the function, and we could use that to come up with the other two factors. So factors are written as x minus whatever the solution is. So first we're going to do this one. It's going to be, now look, this is 5/2 plus 5i square root of 3 over 2. And we are subtracting both parts of that. You can look at this as two different terms. 5 over 2, that's one of the terms. Right now that 5 over 2 is positive, but this is going to switch the sign. And this 5i square roots of 3 over 2, that's also positive. That is going to switch in sign. Okay, so that's one factor. That's the factor that corresponds to this 0. This is the other 0 that we got from the quadratic formula. And we're going to use that to write the last factor. Any factor can be written as x minus the 0 that it corresponds to. So now we're going to subtract both parts of this fraction that you see here. One part is the positive 5/2. This will switch it to negative 5/2, as you see right here. Then we're also subtracting this back term, negative 5i square roots of 3 over 2. And when you subtract a negative, it becomes a positive. And there it is, all factored. We took these two complex solutions, there they are separately, and we subtracted each one from x to get the remaining two complex factors. Okay, last example. Find the complex zeros of the following polynomial function and then write the function in factored form. Okay, this we could actually factor. This is the same thing as having x squared plus 10x plus 9. It's just that these are doubled. And this was also a problem in one of the appendices. How we consider this a trinomial of quadratic form. As long as this power is double this one, you can factor this just as if it was x squared plus 10x plus 9. So remember, when you're factoring a trinomial like this, you take the square root of the first term, which means just take the power, divide by 2. That goes here as well as here. So take the square root of that first term. Okay, then in order to get the back terms, you ask yourself, what do you have to do to multiply? What numbers do you have to multiply to get this constant? But also those numbers need to add to get the middle coefficient. And that's pretty easy. Just 9 and 1. So right now we have this all factored, because you can't factor x squared plus 9 any further. So let's just go ahead and find the zeros. Okay, so I want to know what makes this factor equal to 0. And I also want to know what makes this factor equal to 0. Since these are second degree equations, each one's going to give us 2 solutions for a total of 4 solutions, which makes sense because this was 4th degree, so we need to have 4 solutions. They are all going to be complex numbers, or in other words, imaginary numbers. So here we go. We're going to isolate this x squared term, bringing the 9 over here, and that makes it negative 9. Then we're going to get rid of the square by doing this. Likewise on the other side, but you have to report both the positive and the negative root whenever you're taking the square root of an even-powered variable. Must report both the positive and the negative root. Let me write this a little nicer. Okay, so this is plus or minus. The square root gets rid of the square, and this is plus or minus 3i. So we have two imaginary solutions, two complex solutions, or complex zeros as they call it. Likewise over here, you're going to bring the 1. Over here it becomes -1 with an x squared. We're going to get rid of the x squared by using the inverse operation square root. Likewise, we will also use a square root over here, and we're going to report both the positive and the negative root on the numeric side. So it's x is equal to plus or minus I. Okay, then last, it asks us to write the function in factored form. So, big point here is that every time, if you can't factor something by a traditional algorithm that you've learned, you can go in the back way and you can factor it once you have the zeros, or what we call, the solution, zeros, same thing, by going like this. So, f of x in factored form is like this. For each factor, you're just going to go x minus a 0. X minus the next 0, x minus the third 0, and x minus the fourth 0. You can get yourself set up like that. Go ahead and dump in the zeros. One of the zeros was positive 3i. One of the zeros was negative 3i. And then the next one was positive I and negative I. So this would, I'm just going to clean up the double negatives now, x minus 3i. And I don't think they want you to multiply it out any further, because then it won't be in factored form anymore. It'll look just like that again. So these factors actually show what the solutions were. I believe they want you to leave it like that. Okay, that concludes section 4.7 for MAC 1140.